Hello, everyone, and welcome to this AutoPIPE Tech Talk about working with load combinations in AutoPIPE. My name is Jessica Allegre, and I am a Senior Application Engineer with Bentley Systems for piping. There are many important aspects in performing a successful pipe stress analysis. Pipe stress engineers must make sure the geometry is correct and the correct loads are applied. Even if these loads and the geometry look good, it's also important for the user to understand the load cases and the load combinations that are being used to review the results. In this presentation, we'll discuss working with load combinations in AutoPIPE. So today's discussion topics are understanding load combination options, inconsistent combinations, investigational and typical combination examples, and importing a combination file. So starting with understanding load combination options. After the static analysis is complete, you can review the combinations that will be used to check the model results in the load combinations dialog box. This dialog has 3 tabs. The load case tab is used to review the load cases that were included in each analysis set. The Code Combinations tab displays the combination sets defined for piping code compliance, which will be used to check code stress results. Some default combinations will already be created by AutoPIPE based on the active load cases in the model and the code year associated with the current system. These default code combinations can be modified, deleted, or reset by the user, and also new user combinations can be created and modified also. The Non-Code Combinations tab displays the active load case combination sets defined for any purpose other than code compliance. So for example, to review displacements or support results. Any default non-code combination can also be modified, deleted, or reset by the user. And again, new user combinations can be created and modified here also. It is more than possible, and in fact, it's more than likely, that more combinations will need to be created by the user besides the automatically combined combinations. Loads might need to be combined by the user in order to analyze piping loads on equipment, piping loads on supports, and deflections under various applied loading conditions. Engineers have project requirements that must be met in addition to the piping code requirements. Users can combine individual loads by creating user-defined combinations on the respective code and non-code combination tabs. For the combination name, you should choose something meaningful, such as in this example on the left, we see sus plus E1 plus W1 to combine the sustained case with the earthquake 1 case and the wind 1 case. Next, the user must select the combination method, which is the method that will be used for combining the contributing load cases and/or load combinations from the selection list. The methods shown here are available. So we see sum, absolute sum, SRSS, maximum, minimum, absolute maximum and absolute minimum, resultant maximum, sign maximum, and maximum stress. Next, specifically if you're creating a code combination, the user must select the stress category under which this code compliance combination will be evaluated. In each of these categories, the calculated value is compared to the allowable code value, and overstressed piping will be marked in the results, either by color coding on the interactive scan or by tagging in the output report. This list shows the categories available for most of the common codes. Some codes do have some additional categories available, which are outlined in the program help. So here we see sustained, expansion, occasional, von Mises, hoop, combined, tensile, and hot. Next, the user must enter the name or names of the contributing components of the current load combination that's being created. This can be an existing load case, a combination, or a predefined stress category. The predefined stress category represents the maximum of all of the stresses from combinations that are defined to be of that category type. The maximum stress is added to the stress resulting from the other contributing components. Predefined stress categories are entered using a parentheses around them, such as the sustained case that we see in the top dialog box here. There are some restrictions on the contributing components. The sequence in which the combinations are created determines whether or not a particular combination can be included as a component in another combination. So a combination can be included only if it has been created sequentially prior to the one currently being modified. Of course, a combination cannot include itself, and a combination cannot include a combination that has not yet been defined. This shows the predefined stress categories. Note that if there are multiple analysis sets available, then category maximums, like the sustained, expansion, and occasional cases, will take the maximum stress across all analysis sets. This list shows the load cases in AutoPIPE and how they're identified. So for example, gravity is identified with GR, thermal cases are identified with T1, T2, and so on. Next, the user must enter the factor by which the values of this load case or load combination will be multiplied before being combined with the other contributing load cases, combinations, or stress categories. And this factor can be a positive or a negative value. Lastly, for code combinations, the user must enter the level at which the contributing component is to be combined. And so you can select between M and S. If M is entered, the component is combined at the moment force level. If S is entered, the component is combined at the stress level. This field is open for input only for components which are previously defined load combinations. The default level is for the component to be combined at the moment force level, so with an M as an input. In general, basic load cases such as gravity, temperature, pressure, etc., can be only combined at the moment force level. Load combinations can be combined at either the moment force level or the stress level, and results from predefined stress categories can be combined only at the stress level. For combinations that are calculated in the von Mises or the tensile stress categories, the results can be combined only at the moment force level. So as an example, when a previously defined combination A is combined at the stress level in a new combination B, the moment results of combination A are not carried forward into combination B. So taking that even further, if combination B is then combined at the moment level in combination C, the moments from combination A will still not be included in that combination C because they were not included in combination B. So this allows previously defined combinations to be combined at either the moment or stress level within the same combination, but it can also lead to misunderstanding of the combined results, so it's very important to fully understand this. Going back to the combination method, there are some important notes having to do with the MS option when selecting the combination method. So first, for code combinations, the combination method is applied only to contributing combinations with the MS field set to M. In other words, the contributing combinations that have the MS field set to S can only be combined with other stresses algebraically. The contributing combinations that have the MS field set to M are processed first according to the selected combination method to produce an intermediate combined stress result. This stress result is then combined algebraically at the stress level with the remaining contributing combinations that have this field set to S. Second, the combination methods max, min, absolute min, resultant max, and sign max are always combined at the moment level. Because of this, the case and combination drop-down list will exclude all stress categories. So you won't see sustained or occasional in there for those combination methods. And third, the max stress combination method can only be used at the stress level. So because of this, when changing the combination method to max stress for an existing combination, any individual load cases, gravity, temperature, earthquake, long, or hoop, will be removed, and the remaining components will be set to the stress level. So in this case, the drop-down list for this method only shows valid stress level combinations. Next, let's talk about some important result model options that are available and have an impact on the load combinations. So we'll start with the sustained margin. In this input field, the user can enter either Y, N, or E. If Y is entered, the program will always add the sustained load margin to the expansion allowable stress. If N is entered, the program will never add the sustained load margin to the expansion allowable stress. And if E is entered, the program will add the sustained load margin to the expansion allowable stress only when the calculated expansion stress exceeds the expansion allowable stress without the sustained load margin added. So you can only add Y, N, or E, and E is the default. So as an example, let's look at the code compliance result report if we entered these three inputs. If we have the sustained margin set to E, the code compliance report will show the original calculation without the sustained load margin. But if that calculated expansion stress exceeds the allowable stress, as it does in some cases here, you see that a second line will be added, which shows the calculation including the sustained load margin. If the sustained margin is set to Y, you'll see in the code compliance report, it will only show the calculation of the expansion stress including the sustained load margin. And if it's set to N, the code compliance report will only show the calculation of the expansion stress excluding the sustained load margin. Next, let's look at the use minimum sustained margin option. It's a checkbox. This option allows the user more control on the calculation of the sustained margin and the related expansion allowable stresses. So for B31.1 and B31.3, the sustained margin is defined as shown here, SH minus SL, where SH is the sustained stress allowable and SL is the calculated sustained stress. The expansion allowable stress without the sustained margin is calculated as shown here. The expansion allowable stress with the sustained margin is calculated as shown here. And it's usually written in the code like this. And this is where the SC is the cold allowable stress, SH is the hot allowable stress, and F is the stress range factor that depends on the expected number of thermal cycles. On the right side of the result model options dialog, we have an option that's called number of thermal ranges. In here, you can enter the number of thermal cases to use for ranging. The minimum is 2 thermal cases. If you enter 4, for example, then the first 4 thermal cases in each analysis set will be used in ranging, causing a total of 6 ranges, as shown here. So you entered in 4, so the total number of range combinations is 3 plus 2 plus 1, or 6 total ranges, using T1 to T4. Thermal ranges with respect to the ambient temperature aren't included in this option. For example, the ambient to T1 case, that's generated by default. The valid range of values are either 0, where you don't include any thermal ranges, or 2 to 100. You cannot enter 1 because a minimum of 2 thermal cases are required to generate that range. Lastly, let's look at the max range option, again, another checkbox option. If this option is selected, the program will automatically create a special code combination called max range that stores the results of the maximum thermal stress range case. So that's going between the T1 to T2, T2 to T3 cases, and also that's including the ambient to T1 case type of case too. This option is useful when the maximum expansion stress due to thermal range loadings only is required, rather than generating every single thermal range code combination as we just saw. If this option is checked on, the max range combination will be printed in the analysis summary report as shown here. And in the code compliance report, the max range combination will be printed as TR, followed by the thermal range that produces the maximum stress. So this is where TR is the abbreviation for thermal range. So using this max range option provides the maximum stress range without having to print explicitly the results for every single thermal range combination. Okay, let's move on to inconsistent combinations. AutoPIPE's nonlinear analysis generates results for individual load cases based on the nonlinear load sequence defined by the user. The load sequencing allows the user to define the initial state for an occasional load case. A load combination which considers this nonlinear load sequencing will generate correct results, but a default code combination, non-code combination, or user-created combination, which does not take into account the load sequencing defined for the nonlinear analysis set, may result in inconsistent results. So there's a validation for load combinations implemented in the program, which reports inconsistent load combinations to the user through the consistency check, the analysis summary, and the combinations dialog. The code combinations and non-code combinations tabs of the load combination dialog highlight inconsistent load combinations, and the legend at the bottom shows information for any highlighted combination. So here we see that any combination that is colored in purple is being reported as inconsistent. There is also an option called Show Inconsistent Combinations Report under the Combination Options dropdown, which can be turned on and off, and this will produce a report that will show these combinations being classified as inconsistent. So let's start with reviewing what a nonlinear analysis is in AutoPIPE. A nonlinear analysis is when a user runs a static analysis that includes gaps and/or friction on the supports, or if the yielding of the soil is to be included if there are buried piping points in the model. With these criteria being considered in a static analysis, AutoPIPE will use a method called load sequencing during the analysis to obtain the correct results. This is what's called a nonlinear analysis in AutoPIPE, and it can be set up with specific criteria by the user. So if the user is trying to create a combination that has analyzed load cases from different analysis sets, and at least one of those analysis sets is set as a nonlinear analysis set, this combination will be marked as an inconsistent load combination. The program has implementations for detecting an inconsistent load combination for different scenarios. So we'll go through a couple of them. For a load combination across analysis sets, it starts a loop through all of the load combinations. For each combination, it loops through all of the load cases. For each load case, it stores the analysis set number. If the analysis set number for all the load cases is the same, the combination is, it's possible that it's consistent, but there are some further checks that have to apply. If there are more than one analysis sets, but all the analysis sets are linear, that is a consistent combination. If there are more than one analysis sets and at least one of the analysis sets is nonlinear, that load combination is marked as inconsistent and a warning message will be displayed. Generally, AutoPIPE creates the default code and non-code combinations automatically from a single analysis set. So this check is really useful for trapping the inconsistent user-defined combinations that are created across multiple analysis sets and to report those to the user. Another example, let's look at a load combination that has analyzed static load cases from a nonlinear analysis set and includes more than one occasional load case. So as we see here, it includes two wind load cases. AutoPIPE first starts to loop through all of the load combinations. For each combination, it loops through all of the load cases. For each load case, it stores the type of load, whether it's occasional or non-occasional. If the analysis set number for all of the static load cases is the same and the analysis set is nonlinear and there's a single occasional load case, then the combination might be consistent but needs to go through further checks. If the analysis set number for all of the static load cases is the same and the analysis set is nonlinear and there is more than one occasional load case, then the combination is marked as inconsistent and a warning message will be displayed. AutoPIPE will report inconsistent load case combinations in the combinations dialog box, as we saw with the purple highlighting. In the consistency check report and in the analysis summary report, there is a column for consistency. Next, looking at a load combination from a nonlinear static analysis with the default sequence applied. This section specifically discusses load combinations where all of the load cases are from a single nonlinear analysis set, and there's a single occasional load case being included, so one wind case or one earthquake case, and the use default sequence checkbox for the nonlinear analysis set is checked on. In this case, the program runs through some checks to determine if the combinations are consistent, load combinations, or inconsistent. It checks to see if more than one gravity load case is in the combination, more than one pressure load case is included, and more than one temperature case is included. There are two other scenarios that are also important to consider for these combinations, whether or not the initial case for occasional loads is set to gravity or an operating case. And so, depending on which one it's set to, there are some further checks that the program will run through. And if it does not pass those checks, a warning message will be displayed for these types of inconsistent load combinations. And again, AutoPIPE will report that in the combinations dialog, the consistency check, and the analysis summary. Lastly, looking at load combinations from a nonlinear static analysis with the default sequence option not checked on. So this specifically applies to all load cases from a single nonlinear analysis set, a single occasional load, but this time that use default sequence is not checked on. So in this case, validation of inconsistent combinations would require the initial states information from the initial states dialog box. And if that use default sequence option is not checked on by the user, when you accept the nonlinear analysis dialog box, you will see the initial states dialog box pop up. In general, the default non-code combinations created by AutoPIPE are consistent for these analysis sets. For validation of such combinations, the actual load sequence as defined in the initial states dialog box cannot be violated, and there are checks that run through for consistency based on these initial states. So again, if it is reported as inconsistent, we will see a warning message displaying that. It will also be reported in the combination dialog box on both the code and non-code combinations tabs, in the consistency check, and in the analysis summary. So let's just look at some examples for consistent and non-consistent combinations, starting with the initial states for each load case shown here. This shows some consistent combinations. If we use those initial states, GRT1P1 is consistent because all of the initial state load cases are available. No initial state is duplicated. GRT1, P1, T2, P2 is consistent because all of the initial state load cases again are available, which are gravity T1, P1, and T2. And again, no initial state is duplicated. And going even further, GRT1, P1, T2, P2, U1, user 1, is consistent because all the initial state load cases are available again and none are duplicated. Some inconsistent combinations, for example, are GRT2, P2, because the initial state for T2 is actually P1, and that's not available in this combination. And the initial state for P2 is T2. Again, that is technically available here, but we don't have it available because P1 wasn't available. GRW1 is inconsistent because the initial state for W1 is T1, and we don't see that in this combination. GRT1, P1, T2, P2, E1 is inconsistent. All the initial load cases are available, but the initial case T2 is duplicated in this case, so that makes it inconsistent. And then GRT1, P1, W1 is inconsistent. Again, all the initial state load cases are available, but this time the initial case T1 is duplicated. Okay, let's jump into some investigational and typical combination examples. So we'll just go through some example videos. In this example, we have a support that has gaps. It's a guide support. We have some gaps on it. And we also have a static earthquake load, and we have 2 wind loads too. So we have some occasional loads applied here. So what we're going to do is set up a new static analysis set, and we will modify it to include the gravity load case, 2 temperature cases, the earthquake case, and the 2 wind cases. And in order to include the gaps in the guide, we must make sure the gaps friction soil option is checked on, which will run a nonlinear analysis. We're running nonlinear, so we have to select the initial state for occasional loads. So for this one, we select gravity. And next, we'll duplicate that case, and we'll set the initial state for the second analysis set to OP1, and then duplicate it again and set the initial state for the third analysis set to OP2. So we're looking at 3 identical analysis sets except for the initial state for the occasional loads. We run through an analysis, and we can accept the V-stop liftoff warning messages, and we can review the combinations once the analysis is complete. We know that AutoPIPE automatically creates some combinations, and we'll just look at those. You'll notice that there is E1, W1, and W2 reported in all 3 analysis sets. But remember that they're different because of the initial state that's applied to each one. On the non-code combinations tab, the combinations used for all the results other than code stress, you'll see that in the first analysis set, E1, W1, and W2 are just combined with gravity. In the second one, they're combined with gravity and T1. And the third one, they're combined with gravity and T2, based on the initial state for each analysis set that we define, the user defined. So AutoPIPE automatically combines the combinations correctly for load sequencing, as we saw there. But if you were to create a user combination, you would have to be very careful and make sure that it would be a consistent combination.
Hey, Jessica, we got a good
another example, again, looking at the same model. Let me pause this. Okay, go ahead.
What is the risk of having inconsistent combinations when using AutoPIPE's default combinations?
When using AutoPIPE's default combinations, an example of an inconsistent combination, something that we saw in some of the screenshots that I had, is in the non-code combinations tab. It might just be the thermal case as a standalone case. Technically, that's an inconsistent combination because it's not realistic. It's not a realistic combination. Thermal isn't a standalone case out in the real world, right? It would always be combined with gravity. So technically, the results for that should not be used for looking at things like support loads. It's still okay to use those results if you're looking at like a displacement plot to see how the pipe will move or will grow due to that thermal case. So it's still okay to use it for that, but the inconsistency is basically saying, in that case, don't look at your support loads for this. This isn't a realistic combination. And so it's really just a lot of engineering judgment. So just because they're being reported as inconsistent doesn't mean it's not acceptable to look at some of the results with that case. It just means that according to AutoPIPE's load sequencing, it's not consistent with AutoPIPE's load sequencing. So that's when you have to, as the engineer, decide, okay, let me really understand what this load combination or load case is, and can I really use it to review my results? So it kind of just is a warning to you to take a deeper look at that combination and to understand if it's acceptable or not. Anything else, or continue on, Luke?
Nope, that's great. Thank you.
Okay, so in this example, we're looking at the same model, but this time we're looking at the support that has a friction coefficient of 0.3. So in order to include this friction value, we need to run a nonlinear analysis. We'll use the setup from our first example, and we'll concentrate on that third analysis set with OP2 as the initial state. And we're going to just investigate friction a little bit to decide if it's conservative or not. So we'll duplicate that case, and we'll modify analysis set 4. We see some friction options about including friction in certain cases, and we see a friction scale factor, which we just set to 0 for this case. So that means for this case, the friction will be 0 times 0.3, or 0. We'll duplicate it again, and in analysis set 5, this time, we'll go through and we'll set the friction factor to 2, which gives us a friction value for that support of 2 times 0.3, or 0.6. So we're looking in analysis sets 3, 4, and 5, we're looking at identical analysis sets, except for the fact that one has a friction value of 0, one has a friction value of 0.3, and one has a friction value of 0.6. So this gives us a chance to investigate the friction and to see what value is conservative, to see if maybe as we go towards a higher value or a lower value, it converges. The results start to converge. And this is just showing, taking a look at those combinations after running an analysis set. So there is nothing in here to really show what the difference is, and that might be a good time to use the description option on the right side to maybe add in what those friction values are to show what the differences are between the different analysis sets. Now this is important because friction is going to exist at all supports where some movement is permitted. The friction can prevent the free expansion movement of the pipe through the support and create higher stresses in the pipe and higher loads at equipment if this piping is attached to equipment. But in some instances, the friction can serve as a guide, and it can prevent static loads from being transmitted to equipment. So it's unclear whether it's conservative to include or to ignore friction for static analysis. There really is no rule of thumb to deal with friction for static loads, and the effect of friction should be investigated to simulate as closely as possible the real-world situation. So in AutoPIPE, as we see here, it's very easy to run these investigational analysis sets to determine the conservative approach. Okay, continuing on, we now have a third example. We're going to look at a pump farm example. So in this example, we have piping that's connected to 2 pumps, and using the show options, we can see based on the operating temperature, in operating case 1, pump 1 is on, so it's operating at 400 degrees Celsius. In case 2, pump 2 is on, and in operating case 3, both pumps are on. So let's assume we want to consider each situation as an individual analysis set for organizational purposes. We can create analysis set 1, just including gravity and T1. We can then create an analysis set number 2, where we just include gravity and T2. And similarly, we can create an analysis set 3, where we're including gravity and T3. And we can run the analysis. After the analysis is done, of course, we want to review our combinations. And on the Code Combinations tab and the Non-Code Combinations tab of the Combinations dialog box, we have defined this as having a different analysis set basically for each different situation, each that 1 pump's on or 2 pumps are on. So what would be useful is to actually write what situation each combination is representing. And I mentioned this in the friction example too, but here we'll just see if we write in pump 1 for the first case analysis set, pump 2 for the second analysis set, and pumps 1 and 2 on for the third. Any type of description that you want, but it would be useful to actually write that in there so that you can distinguish between the differences between your analysis sets. Okay, let's look at our fourth example. Again, looking at the same model, but this time, so go ahead.
So the question is why does AutoPIPE not offer an option to ignore friction for wind like they do for seismic?
I believe that's an enhancement request. Luke, can you comment on that?
I haven't. I don't recall that being a recent one, but I mean I can definitely add that. From what I recall, the seismic has the option to ignore the friction because in a seismic event there's more of a vibration, there's more of a chance for that pipe to bounce off of the pipe support. That's why that that option is there for seismic events, not necessarily for winds, but we can definitely add an enhancement request in the future for that.
Yeah, and I'll add that I believe I was just recently on the wiki page for these types of loads, and I believe there is a workaround on our AutoPIPE wiki page for turning it off for wind. So if you just take a note of the user, maybe we can follow up and just send that wiki page.
Right. And then we also had another user asking kind of an unrelated question, but he was asking for an enhancement regarding pressure extension for hydro test. That is an enhancement request that I'm familiar with, and we'll try to get it added to a backlog as soon as we can.
Okay.
All right, back to you, Jessica.
Oh, okay, continuing on. So this is the fourth example. Let's just run through it here. So here we're going to look at adding a user load case to the piping model. User load cases can be used for some occasional loads like wave loading. And they could also be used for some extra data types of loads. So in this example, what we'll do is we're going to first add a point along the piping between C60 and C65. And at that point, we're going to add an additional weight. So adding an additional weight enables the user to define the weight or a point load of a non-standard or a special component at a specific point. The weight is automatically, in this case, included in the gravity load case, so in the GR load case, and it always acts vertically down. Next, we'll look at, in this section of piping, adding a distributed load. And the distributed load command works a little bit differently. This enables the user to define or modify a linearly distributed load over a specified range of points. And the loading can be added to any one of the defined static load cases. So here we see we're setting it to a U1 load case, which is a user load case. So it gives the user control on how you're combining it. So let's look at how it gives us that control. So we'll set up a static analysis set. And we want to make sure to include that user load for the distributed load. So we're going to include gravity, temperature, and the user one load case. And just including a T1 case just to keep it simple. Not too interested in the initial state for occasional loads here, but we'll set that to OP1 and we'll run the analysis. So going to our combinations after the analysis is run, if we go to the Code Combinations tab, we're going to see a sustain plus U1 occasional case. And we can double click on that case in order to see what AutoPIPE combined to create this case. And we see that there is a sustained stress category plus the U1, which is our distributed load. So if we look at what was combined to create the sustained stress category, that's gravity plus long. So what that sustained plus U1 case is including for us is our gravity, our additional weight, and our distributed load. But it's important to understand some of these types of loads and extra data is automatically included with gravity. So every time you see GR, that additional weight is applied. Make sure you completely understand that. And every time you see the U1 case, that distributed load is applied. So maybe adding some description notes to those types of load cases would definitely be useful also. Luke, you have a question?
Question, Jessica. What does the offset point mean in the weight window?
I have to go back. In the additional weight. Oops. So the weight will be applied automatically in the vertical direction, but I believe that gives you the ability to actually apply it in a different direction besides the vertical direction. So if you want that additional weight applied in the horizontal direction, you would have to actually put that. Oh, I'm sorry. No, I'm incorrect. So offset from the point is actually the direction along the piping. It doesn't have to be at the center line of the pipe, the additional weight. So let me correct myself. So the offset from the point is I'm at a point. I'm specifically at, in this case, this point here. And you can offset it in any direction from that point the additional weight that you're adding in. So it could be considered an eccentric load also. Okay, so just finishing up, we have one last topic here, which is importing a combination file. While AutoPIPE automatically creates load combinations required by the code, as we've seen, and you have options to create user combinations, as we've seen, there are also many other combination options that users are unaware of. One of the options is being able to import a combination file created by the user for code and non-code combinations. So users can import combination files that include whatever combinations they choose or need to include. And this is helpful in a project where all users should be checking results in the same combinations. And it saves time to have, rather than having to create them in each model. So I always say if you have multiple users, it's very useful for maybe management to create a combination file and distribute it to those users and say, hey, use these combinations. But even if you're an individual user and you're working on 20 different models and you want to look at the same combinations for results in 20 different models, it's even useful in that case where you can just import the combination file. So the user can import both code and non-code combinations from one model to another model. In AutoPIPE, the combinations for a model are stored in a .cmb file. The option import combinations from file allows the user to create the user combinations based on the user combinations from a different model. And this option invokes a file open dialog box where you can select a .cmb file from a different model whose combinations are to be brought into the current model. Just some points to consider. If the load cases used in the combinations of the source model aren't available in the current model, the combinations will be marked as invalid, or you'll see that they will be shown in blue because they don't apply to your current model. And all of the existing combinations are removed before importing the new combinations. So you'll lose whatever you currently have if you did need those combinations. There is a confirmation message that pops up to warn you about that, but just make sure that you actually want to completely replace the combinations that you currently see in this dialog box. Just as a review of today's topic discussion, we went through understanding load combination options. We went through the 3 tabs in the combination dialog box, creating code and non-code user combinations, and the result combination options. We looked at inconsistent combinations. Some examples, we went through load combinations across analysis sets, nonlinear static load combinations with occasional load cases, and with the default sequence checked on and checked off, and we looked at some consistency examples. We went through investigational and typical combination examples, so looking at nonlinear static load combinations with different initial states for your occasional loads, looking at investigating friction, a pump farm, and user load cases, and we discussed importing a combination file. So in closing, I just want to draw your attention to a great resource for anyone wanting to learn more about Bentley pipe stress products. We have a YouTube channel that has a variety of videos covering all aspects of our products, and each week we add more of these. So if you're interested to see what's new or how to use a certain feature, subscribe and search for the Bentley Pipe Stress Analysis channel. And if there's something you wish that there was covered, feel free to please drop us a line. We're always looking for ideas for additional content for YouTube videos and different sessions. Thank you very much for your attention. If you have any questions, sure, go ahead.
So what is the purpose of the cut short option in the analysis set?
In the extra data, the cut short option, to my understanding, is used often when you're connecting to rotating equipment, and it's used to even out the hot and cold stresses. So sometimes if you're connecting to rotating equipment, you might have really high hot stresses and really low cold stresses. And the cut short does just that. It actually cuts the pipe short a bit, and it creates some it creates an more even cold and hot stress.
Okay. One question we had was, do you have these topics covered in the user's manual?
I'm not sure.
So
we don't necessarily have a user's manual. We have all of our the topics that are discussed here are in our help content. So if you go to the help menu, whether you're using an old V8i version or the new Connect edition, you go to the help content, and all of these discussions were covered in our help content. Another good source for help is our Bentley Communities website, forums, and wikis and such.
Yeah, and I'll just remind everyone of the option in each. So if you're asking about a specific thing I presented on, if you're in that dialog box, remember that there is a question mark on the top right of the dialog box. And if you click on any input field, it will bring up that specific context help. And it's very, very useful to use that. So I'll just remind everyone of that. And the help button in the bottom of each dialog box is very useful.